All right. So you have been learning about series. A series is a sum of an infinite number of terms from a sequence, and sometimes series will converge, sometimes series will diverge. And in section 8.2, you learned about some very well-known series such as geometric series, harmonic series, telescoping series. And in section 8.3, you looked at series that are a little bit different. They're not your standard series overall, but nevertheless, through different kinds of tests, we can determine whether those series converge or diverge. And in section 8.3, all the series, the terms of the series were all positive. So we could use like an integral test, or, well, we could try an integral test or a comparison test or a limit comparison test um, to determine convergence or divergence of those series. And sometimes one test will work while another test will not work. Okay, and you have to be very careful on those kind of problems because the way WebAssign has it is it's either you have one chance to get it right, so you got to be careful before you say converge or diverge. And then also in section 8.3, we learned about when a series converges and all the terms are positive and they meet the conditions of the integral test, we can estimate the sum as well. So this is all great stuff, great material, but we need to expand our horizons a little bit. Like it says here at the top of section 8.4 in the ebook, the convergence tests that we have looked at so far apply only to series with positive terms. In this section, we learn how to deal with series whose terms are not necessarily positive. Okay, so it allows for series to have negative terms as well. So the first thing that you need to recognize is an alternating series. So an alternating series is a series whose terms are alternately positive and negative. And below, they give you two examples of an alternating series. So take a look at those. I mean, I think it's pretty clear. They're writing out, they're writing out some terms of the series, and then they're writing a formula to describe that series, a summation formula. And those are examples of alternating series. And right now, you don't know, you don't have any tests that will work to establish convergence or divergence of an alternating series, because the tests that you learned in section 8.3 deal with series that have all positive terms. So if we go down a little bit here, okay, they have a test called the alternating series test. Okay, so the alternating series test is basically, I have it right here. Maybe I'll highlight it. This is what the alternating series test is. Let you read it for a moment. And I saw a, okay, very good, very good. Okay, so all right. So Mandy, I can answer that question at break. Okay, I think help you answer that question at break. So here is the theorem, alternating series test. If you have an alternating series, okay, and they write the general form of the alternating series as the sum where n equals 1 to infinity of -1 to the n minus 1 power times b sub n, and they write out the terms of the series. The b sub n is like every term of the series and not regarding whether it's positive or negative. So that series will converge if two conditions are satisfied. So condition 1 says that b sub n plus 1 is less than or equal to b sub n. Well, what that means is that the terms of the series are decreasing. Okay, the terms of the series are decreasing. And the second, or eventually they're decreasing. The second condition of the alternating series test is that the terms of the series has to equal 0. So remember, the harmonic series, for instance, satisfies these two conditions, conditions 1 and 2, because the harmonic series, the terms of the terms of that series are decreasing. Okay, and the terms of the series are approaching 0, but all the terms are positive in a harmonic series. But if you have it where your series is alternating from positive to negative, and so forth, essentially what happens is the negative terms deduct from the positive terms, and so it gives the alternating series a better chance of converging. That's essentially what that means. So, I mean, for example, let me just go to the whiteboard and I'll give you an example here. Let's focus on that that alternating series. Yeah, Masume, question?
I'm sorry, I accidentally touched that.
Oh, no problem, no problem. Okay, so yes, Clay. Yes, Clea. Yep. Question. All right. Well, what I'm doing is I'm writing down some terms of what kind of series is this? This series that I wrote down here. What is that series called? That's right, Yonatan. It's a harmonic series. All right, and it's a harmonic series. And it diverges. Okay. Now, if I write down this series, 1 minus a half plus a third minus a fourth plus a fifth minus then dot, 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 you know. This series has this formula. So you need the negative 1 to the n minus 1 power to so that you can get the terms to alternate from positive to negative. All right. Now this series, this second series almost looks like a harmonic series, but it's not. It's what we call an alternating harmonic series. And that series, in fact, converges. So just the fact that you put in this negative 1 to the n minus 1 power so that the terms, go from positive to negative, positive to negative, they alternate. That would allow that series to converge because the 1 over n is your b sub n. So by the alternating series test, this series converges. If I go back to that alternating series test in section 8.4, if I go back to it here in the ebook, Well, actually, hold on. There's the alternating series test, and there are the two conditions. They're the two conditions. So those two conditions, if I go back to the whiteboard, they're satisfied, okay? Because, let me just separate this a little bit here. They're satisfied because by the alternating series test, that's right, Clay. Both conditions need to be satisfied. Condition one is satisfied because the B sub n, which is 1 over n, I'm going to phrase it my way. B sub n, which is 1 over n, decreases with n. Decreases with n. So check on that. And then the second condition is that as n goes to infinity, the nth term, which is 1 over n, approaches 0. So the terms are decreasing and they approach 0. And so for this alternating series, this alternating harmonic series converges. The regular harmonic series diverges. Okay. So that's an example of how you can use the alternating series test. Okay, are there any questions on that? Yes, Jonathan.
I don't understand how the first condition is met. For b sub n plus 1 is less than or equal to b sub n for all n values.
So another way I could phrase this first condition here is this. I could phrase it this way. Let me just, so this first condition, like 1 over n plus 1 is less than 1 over n. 1 over n plus 1 is b sub n plus 1. 1 over n is b sub n.
Oh, okay, that makes sense.
But, you know, you could just say, I mean, the terms decrease with n too. That would be another way to phrase it. But okay, good question. Good question. Clea, question? Okay. Okay. Well, I'll tell you what. Let's go look at some examples here. So this is like the first example. And incidentally, I guess I would be a little bit like in the ebook here. Okay, they prove here why this alternating series test is true, and they do it based on the fact that if you were to look at partial sums of the series, you see on that axis there, they have these partial sums. The first partial sum, which is just the first term, b sub 1. The second partial sum, which is b sub 1 minus b sub 2. Third partial sum is b sub 1 minus b sub 2 plus b sub 3. And what's happening is as you subtract and add terms, it moves the partial sums about that sum s. But since the terms are getting smaller and smaller, eventually the partial sums have to essentially converge to the middle, which is that final sum s. So Figure 1 just shows an intuitive way to understand why the alternating series test is true. All right, let me see here. Let me bring up. Okay, so here's some examples, and we actually did the first one, but nevertheless, let's go ahead and let me give you a moment to copy this example down, and then we will discuss the example, discuss the solutions. So these are very interesting series in A, B, and C, and you can well, we'll take them one at a time here. We'll take them one at a time. Okay, so the first series, well, no, let me give you another minute here to copy. Okay, so the first one, A, is this series here. We just looked at this one. It's that alternating harmonic series. Let me just show you the solution for that. Hold on. There it is. So if you want to formally write the solution, here it is. If you have any questions, let me know. We already talked about the solution, but go ahead and copy copy it down. Please let me know if you have any questions. So a lot of times the alternating series test, you can almost just look at the series and I mean, the conditions are so easy for the alternating series test that they're so basically easy to establish. You can almost look at the series and intuitively, if it's a simple alternating series, you can almost verify those conditions 1 and 2 are true just by looking at the series and using, your common sense. So students tend to really like the alternating series test because it's usually very easy to use. We like to use it in situations that are very easy. Okay, now let's go back here to this second series. So the second series here, series B, this series, is this an alternating series as well? Indeed it is. Indeed it is. What makes it, that's right, that's right. Very good, Jonathan. So this second series here, notice you have the, hold on, I gotta change my font here. I don't know why it has it. Yeah, because of this term here, -1 to the nth power, that's gonna go negative, that's gonna go -1, I mean +1, -1, +1 in this case. So it'll make the terms of the series alternate. So the terms of the series alternate. And let me ask you, does this -1 here matter much? Does that affect the values of the terms of the series when n is large? It does not. It does not. That's right. That's right. So essentially, you're focused here on the 3n over the 4n, right? And 3n divided by 4n equals what?
3/4.
3/4. That's right, class. So 3n divided by 4n, the n's simplify out, and you have 3/4. So the terms of this series for n is large are going to start behaving like 3/4, -3/4, +3/4, -3/4, and so forth. And so the series never has a chance to, it'll never converge. Let me be a little more formal here. Here's the solution. What we're really using is the test for divergence, which you saw back in section 8.2. The limit of this series just does not exist. It does not exist. So this series diverges by the test for divergence. The series, as n goes to infinity, this series behaves approximately like taking 3/4, -3/4, +3/4, -3/4, and that there's no settling down there. The series diverges. Jonathan, question?
Would this satisfy the other condition though? Like I know you need both in order to say it diverges, but would this satisfy the other condition of b sub n is less than b, or sorry, b sub n plus 1 is less than b sub n? Like, is there a way that you could test that, or is it just there's no point because we know that the limit doesn't exist, therefore it doesn't equal 0?
There's no point because we know the limit doesn't exist. That's right. Well, let me ask, no, actually we can, the second condition, okay, good question. No, we can actually, hold on, that's a very good question. We can actually, the alternating series test, so the, for this problem, hold on, let me just clear this here. So B sub n would be 3n over 4n minus 1, right? For the alternating series test. What's the limit as n approaches infinity of B sub n? Three-fourths, which is not equal to 0. Not equal to 0. So therefore, by the alternating series test, I want to be a little careful. Yeah, it's not going to work. Yeah, it'll diverge. So you could use the alternating series test. They just, they want to put names on. I mean, they like to. Well, it's helpful to have names for things. It's helpful. But all right, are there any questions on B? Okay, well, let's go back here. Let's go back to this third series. Now, this third series, okay, I wrote out some terms. Is that an alternating series?
No.
Well, you're right, Clea. You might think it's alternating because, like, for instance, the first term, if your calculator's in radian mode, right? Calculator in radian mode. The first term here is going to be positive 0.5403. Okay, the next term, cosine of 2 over 2 squared, that's going to be, well, that term's going to be negative 0, hold on, negative 0.4161. So far, so good. We have a positive term and then a negative term. But if we look at the third term, cosine of 3 over 3 squared, and our calculator's in radian mode to compute this, that's going to be negative 0.990. So you see, this series, it started out alternating, so far so good with the first two terms, but now the third term was negative. So because the second term was negative of the series and the third term of the series was negative, you don't have a strictly alternating series. So that means you cannot use the alternating series test on this. So how are we going to handle this? Well, let's go to the solution here. I have this formalized in the solution. We're going to have to look at something called absolute convergence. But let me give you a moment to copy down to here. Okay, and then I'll talk a little bit. All right, so let's think here what we have. We have a series that, I mean, so far the only like to establish if a series converges, the only test we have for, like if we have a series that has positive and negative terms, the only test we have is the alternating series test. I mean, that's the only test we have learned really in section 8.4. But because this is not a strictly alternating series, we can't use the alternating series test. So what we're going to do is we're going to look at the series where we have the absolute value of the terms of the series. So you notice that I've taken the cosine of n over n squared, and I've put absolute value signs around that for the term. So in other words, what I'm looking at is this series here. But the idea is if this series converges, if this series converges, where we're adding up the terms and we have absolute value of the terms, so they're all positive. If that converges, then so does the series where we don't have the absolute values of the terms. You see? In other words, what do we worry about with the series? We worry if the sum is infinity. Well, the series where you have the sum of the absolute value of the terms, that series would have to have a larger sum than the sum of the series where you don't have the absolute value of the terms. And so if the top series where we have the absolute value of the terms, if that series converges, then the other series here must converge. Okay? I mean that, and this is the concept called absolute convergence. So look at what we do here. We have the absolute value of the cosine of n over n squared, but that would be less than or equal to 1 over n squared. Okay, so what I'm going to do is I'm going to try to establish convergence of this series here. This series here. Now, the cosine of n, the absolute value of the cosine would never get greater than 1. We know how the cosine function oscillates between 1 and -1. Now, I'm very happy when I see 1 over n squared. I mean, what am I trying to do here when I have the absolute value of cosine of n over n squared is less than or equal to 1 over n squared? What do I have in mind here? 1 over n squared. How am I going to, why am I happy about seeing that?
Because we can use a series that we know if it converges or diverges, so that we can decide the one we want to.
That's exactly right, Claire. That's exactly right. And Jonathan mentions that it's a p-series. We're going to be dealing with a p-series. So you're both right. And so let's go ahead here and say, okay, well, I want to say this the right way. Hold on one moment. So I'm saying here that the absolute value, the series where we have the absolute value of the cosine of n over n squared, those terms, that converges. This is by the comparison test. Since the p-series converges. The series n equals 1 to infinity is a, the series from n equals 1 to infinity of 1 over n squared is a p-series. It's a p-series with p equals 2, which is greater than 1. So the p-series, this p-series, by virtue of the inequality that we had on the previous page, this p-series is larger than the series we're interested in. So since the p-series converges, this series n equals 1 to infinity of the absolute value of the cosine of n over n squared, that series converges. So if that series converges, then surely our series n equals 1 to infinity of cosine of n over n squared has to converge as well. I mean, you know, because it wouldn't be as big a value, right? Because some of the terms are negative. Yeah, question, Clea? Good question.
Yeah, so can you just explain why do we say that the series absolutely converges?
Well,
We say absolutely.
yeah. I'll explain that. I'll explain that. Okay, I'll tell you what. I'll go to the whiteboard and mention that. Let's make sure. Let me give you a moment to copy this, and I'll go to the whiteboard for further clarification. Okay, may I go to the whiteboard? Everybody has this copied okay? All right, let's go to the whiteboard here. So what we have here is we have this series. Okay, and all right, and we don't know, we don't have information about that series. Okay, but if we look at the series, maybe I'll put it in red. If we look at this series, where we take the absolute value of the terms, okay, this series converges because the terms of this series are smaller than the terms of the p series with p equals 2. So this series converges. If this series converges, this implies then, that's going to imply that the series we're interested in also converges. You see that that's called, we're using absolute convergence to, it converges. As a matter of fact, we say it converges absolutely.
Yeah, do we say that because I was thinking about it, and so if you're using the absolute value, that's why we say it absolutely converges?
That's right. That's
Okay.
right. If a series converges absolutely, then the series, when if we adjust the series to make all the terms positive by putting in the absolute values, that series converges. And if that series converges, our series converges. So if a series ever converges absolutely, it converges. That's right. Okay. Let's look at another one here. Let's look at another one. Let me go a little bit further here. I know we're going to take a break, but I want to do one more before we, at least, let's go to these examples here. Let me give you a moment to copy this example down. So of these two series, which series is the strictly alternating series? Series A or Series B? Good, Series B, because you have that -1. Good, Susanna, good, Jonathan. You have that -1 to the nth power there. What do you think for Series A? What do you think we're going to do to establish if that series converges? The sine of 4n, okay, what's the most that could ever be? The sine of 4n. All right, Jonathan's saying, well, it could go, but what's the greatest the sine of 4n could ever be? So a sine wave, a sine of any angle, the sine is always bounded between one good, that's okay, between 1 and -1. So that means if we were to take the absolute values of these terms in part A, we could bound them. We could bound them. And that means, oh, use comparison test. So let's go here to the solution. Here's what we do. We look at the absolute values of the terms. We look at the absolute value of the terms. And the absolute value of sine of 4n over 4 to the nth power is less than or equal to 1 over 4 to the nth power, and that is equal to 1/4 to the nth power. Well, we recognize the series n equals 1 to infinity of 1/4 to the nth power as a convergent geometric series. And so by the comparison test, the series where we take the absolute value of our terms also has to converge. Because remember, this often helps me, but this series is less than or equal to the geometric series. So if the bigger series converges, and you notice both series have all positive terms, so you can use the comparison test. Oh man, hold on. Hit the wrong button again. Boy, hold on, there we go. Learning how to deal with that. If this larger series converges, that implies that the smaller series converges. It's that simple, really. And our series then converges absolutely, and hence convergence. Absolute convergence is a higher standard of convergence. So if the series converges absolutely, it has to converge regularly, so to speak. It's really a very beautiful concept, and it helps us deal with situations like this. Are there any questions? All right, well, if you're good with that, then what I want to do, we have another one to do, right? We have this B to do here. Okay, this series here. And let's take a 10-minute break. We're going to keep our break a little shorter this time because we really have to get this section covered today. Let's take a 10-minute break, and when we come back, we will finish up this example and look at the series B. Okay. Are there any questions before we take our break? Are we good? Okay, I'll stop the recording then.